Perfect, and we can see that. Okay, great. So our next speaker is Austin Gabrielpillai, talking about semi-analytic bubbles with deep mock Roman surveys. So go ahead, Austin. Thanks.
Great. Yeah. Um, just to reestablish, yeah, my name's Austin Gabrielpillai. I'm a graduate student, part of the MS in Astrophysics program at the CUNY Graduate Center. Major thanks to the organizing committee for letting me doing this talk remotely. And today I'm here to talk to you about making reionization bubbles with the semi-analytic modeling. So just kind of as a quick recap for those of you who are familiar slash unfamiliar with reionization is like the last major phase transition of hydrogen in the universe, where ionizing radiation produced by a variety of sources turned the neutral intergalactic medium, IGM, into an ionized medium, which then subsequently allowed that ionizing radiation to traverse across the universe and eventually reach us, giving us what we see today. And these sources of reionization include the first stars, POP3, first galaxies, and then also quasars. And so Roman is set out to be a unique instrument for helping us understand how this phase transition occurred over what time scale, due to the combination of having such a wide footprint and these mid-infrared filters, right? Notably, both Hubble and JWST have seen evidence of ionizing reionization bubbles around galaxies, and so Roman should also have this capability. Thus, it's worth considering what we need to do for Roman in order to be detecting these bubbles with mock surveys and planning and whatnot. This leads to a unique problem, though, in that we need both wide and large simulations with multi-scale physics, to characterize reionization and make predictions for Roman. And these simulations, which have been historically fully hydrodynamic with radiative transfer, large-scale boxes, have been computationally and time expensive, taking millions of CPU hours. So our aim with this project is to see if we could use semi-analytic models of galaxy formation to do fast reionization simulations so we can make predictions for Roman. And we accomplish this through a threefold strategy in that, one, we calculate the ionizing photon production per galaxy from rich star formation histories. Two, we make reionization maps of the IGM with variable escape fractions, so we can vary that for different case scenarios. And three, extract and make statistics of the reionization bubbles we get from our map. And so to briefly talk about the SAM, because Aaron has done a great job of explaining the semi-analytic model for galaxy formation that we've used. This light cone is the same light cone that he spoke about in his talk, where as part of his paper forecast series. This light cone spans redshift 0 through 10, has a lower mass limit about 10 to the 10 solar masses when it comes to halo mass, and 10 to the 7 solar masses when it comes to stellar mass. As well as the footprint being 2 squared degrees. And the data catalogs that are part of these data releases, which include galaxy and halo catalogs, photometric predictions for rest frame and absolute magnitudes, as well as star formation histories. So this graphic I have kind of like emphasizes the strength of the light cone, where this bottom panel is a look back through redshift and physical space, colored by absolute UV magnitude. And this gray slice represents these two top panels over here. It's the same slice taken at redshift 7.25. This left panel is the instantaneous star formation rate of these galaxies. And then this right panel is a Roman filter's observed magnitude. So coupling all of this information together gives us the ability to make very strong predictions for Roman. And so as I've mentioned, one of the data products created through the SAM is star formation histories. And this is a grid of both ages and metallicities, where given an age and metallicity bin, the SAM is able to tell you how many stars of that metallicity and age in that mass were produced. There are 12 metallicity bins and then 197 age bins in semi-log spacing. These age bins are inherited from Bruzal and Charlot 03, because that was the initial age grid that Aaron used to produce photometry. But using these age bins and metallicity bins. We can then convolve it with ionizing photon production tables to then get a total ionizing photon per galaxy. And so the first row here in this graphic shows you a demonstration of the age of metallicity bins, where you could see at high redshifts for the SAM, for this redshift 6 galaxy, you have stars that are produced with very low metallicities around redshift like 15 through 17 or so. And then as you evolve through time, you start to see more and more enriched stars that are produced. And so we convolve this information from this grid with ionizing photon production counts from the BPAS star population synthesis model for both binary and single star populations to get the ionizing photon count per age bin, as seen in this middle row for here. To which then we now need to factor in hydrogen recombinations, which are when your ionized hydrogen are returned back to the ground state of neutral. And so we have to then filter out the populations of ionizing photons that have recombined. So any age bin that is greater than the recombination time has been zeroed out. And then we then do like a fractional calculation of how many remaining ionizing photons are left for the remaining age bins. And then lastly, this last row shows you a cumulative distribution function of our ionizing photon counts, and is showing that most of your ionizing photons come from your young stars. So this is a first look at our bubble simulations. This is a qualitative visualization for 3 different escape fraction scenarios. We're looking at 20% at the bottom, 50% in the middle, and then 80% at the top. And this is looking as a slice through redshift space. So we're going from like redshift 9-ish to 6.5 or so. And this helps kind of understand what we're trying to work with when we're eventually making slices through the IGM to make our reionization maps. It gives us an idea of what type of structure we'll be finding, what types of bubbles, and then how the escape fraction affects that. For example, in low escape fraction scenarios, you can see centered around 7.2 or so, you have, these lovely island chain of bubbles, but then as you get to higher and higher escape fractions, these end up combining into these larger, as I like to say, mega bubbles. And so here's a footprint visualization for when we do take a slice at specific redshifts. This is a bubble simulation done at redshift 7.25 in this graphic. To get into details, we ran our simulation on 150 redshift slices. It took about 2 days to run on my personal laptop with Numba, but no parallelization across CPU cores, so there's a lot of room for improvement there. Overlaid onto this graphic are 2 sets worth acknowledging, or 3 sets. First is that the scatter is different galaxies that live at this redshift slice with plus or minus some delta Z. Second is various telescope footprints, which include HST Hubble Wide Field Camera 3, JWST NearCam, and then, of course, our lovely favorite Roman Smiley Roman Wide Field instrument. And then third, it's showcasing our various contour levels that correspond to different escape fraction scenarios. On here, we have escape fractions for 20% and 50%. And the reason we could do this is, as I've said before, we've left the escape fraction as a free priority to help guide us into what we're trying to see for our observable universe. And so Roman, as shown here, is in a unique position, is that it's able to capture both large and small bubbles, as well as their bright sources that come along and produce them as well.
You have 3 minutes.
Okay, so I'll hurry this up. How do you extract bubbles from these maps? I am taking inspiration from hydrosims using something akin to a friends of friends algorithm, where identifying local minima in those maps tells us where our most ionized cells are. And then from there, I can look at their neighbors, see if they're also ionized based off of our escape fraction threshold, and then assign those to those minima, and eventually getting a catalog of bubbles as well as a bubble segmentation map. To which then, from that area ionized, we can then back out an effective radius. And so here's some beginner statistics that we've been looking at for our 3 escape fraction scenarios, 20%, 50%, and 80%. This top left panel is looking at the total area ionized versus the total area as a function of redshift. And we're trying to see that for our 80% scenarios, the closest that we get to a total ionization, total reionization of probably close to 96, 97%. This next panel is then looking at the number of bubbles as a function of redshift, to which you could see where I've pointed out where all these bubbles have percolated into a large mega bubble in the 80% case scenario. And then we're also looking at how these bubble sizes evolve through time for medians and means. Some last caveats on considerations. As I've mentioned, we're only looking at these large halos, so we are missing these smaller halos, less than 10 to the 10 solar masses, which is why we need such a high escape fraction to achieve full reionization in our simulations. Our results are comparable to one of the Thieson hydrodynamic reionization runs, Thieson-high-2, which also doesn't reionize the universe under similar halo masses and escape fractions. And
1 minute,
again, we
Austin.
are using a simplistic IgM. And so some last conclusions is using these data-rich star formation histories, we're able to look at the structure of reionization over large areas. And without low mass galaxies, we have to have a very high escape fraction, and there is significant structural changes that we're able to do predictions for over our large field. And then last, we can be able to assign galaxies to bubbles, mapping photometry for Roman survey predictions. So yeah. Questions? Answers?
Great. Thank you, Austin. Are there any questions? Yep, up front here.
So I can see how Roman survey will be good for helping you find the sources at high redshift. What things are you hoping you can look at to actually map the bubbles? Is the notion to use GRISM to look for Lyman alpha emitters at these redshifts, or some other strategy?
Yeah, that's a great question. And yes, we were hoping to use GRISM simulations in tandem. We've been working on that, as well as next steps include trying to do Lyman alpha production as a proxy with star formation rate to see to what bubble sizes we can expect by doing this galaxy mapping to bubbles and whatnot.
And the back there, Aaron.
Hi, nice talk. So I'm wondering about the escape fraction. You're using a single value for all halo masses, is that correct?
Yes, right now we are using a single value for all halo masses. However, the flexibility of our model will allow us to consider escape fractions for different halo masses, a time-dependent escape fraction and whatnot. So just for the sake of proof of concept, though, we have been using a single constant fixed escape fraction, but there is room for variability in different directions.
Okay, sure. So I guess future work then.
Yes.
So how exactly do you put the bubbles on? Are these sphere cutouts or some kind of
Yeah, so going back, you could kind of see where with these contours, right? Using, for example, I guess this very nice round one around -12 and 10, yeah, or so. The contour values in there are the cells in that contour are effectively considered ionized. So then when we go in, we can look at that area of all these cells, to which then we can back out an effective radius. Yeah, we're kind of using 2D cutouts to get these bubble sizes, which
right? But how is the original bubble put on the ionization state determined? I just wonder, when you have overlapping bubbles, you have to conserve photons and things like this.
yeah, so we do kind of like a volumetric assignment. So given a galaxy's distance to a cell, we consider its contributions, and then we do a 2D search across all galaxies that live in that slice to then say, okay, these are the contributions from all possible galaxies to that cell, and then that's how we end up with overlapping bubbles, as you then see.